Okay, everyone, so we're back to inductors again, but now we're going to be looking at inductors in AC circuits. And eventually in this presentation, we'll look at combining resistance with inductors to give us a total AC load that is combining the two forms of opposition. So before we get started, I actually wanted to just kind of define something called impedance before we get started. So we know in a DC circuit that all of our opposition comes from components that are resistive. So in a DC circuit, we were always talking about total resistance. And total resistance was our total opposition. And remember, when we were determining values of R total, that was one of our starting points in circuit analysis. We would redraw the circuit if necessary to give it its simplest form. We would determine the total amount of motivating force, or the E total value. And then the next thing we would do is move on to an R total value, or a total opposition. Well, when it comes to AC circuits, the process for analysis, the steps that you take are really no different. But instead of resistance now as being your opposition in an AC circuit, we call it impedance. So this is impedance. And impedance is really defining AC opposition. Okay, now we can't call it R total anymore, so impedance is equal to Z. So we have Z total as our total impedance. Now the thing about impedance is Z is equal to resistance and reactance. Now reactance can come from a capacitor or an inductor, or it can be both capacitance and inductance, where we have a net reactive value. But for now, what we are just defining is that impedance Z can be all resistance, all reactance, or in most cases, total impedance in an AC circuit is a combination of resistance and reactance. So when it comes to a value of Z, or total impedance in a circuit, there's two ways that impedance can be represented: as a rectangular value or as a polar value. So as an example, a rectangular value would be an R plus J XL value, where the XL is coming from inductive reactance. So this is a primarily inductive circuit as far as reactance goes, and we have a Z total value of the resistance plus the plus J value, or imaginary component, plotted as XL in your total impedance. Well, at the same time, that can be expressed as a Z total value at an angle of what's called phi or phi, defining the angle of impedance. So when converting from rectangular to polar, or polar to rectangular, you'd be getting these two forms, or these two expressions of total impedance. So I wanted to talk about that before we started into our presentation on inductors in AC. So when it comes to an inductor in AC, and we look at this slide here, we've got a representation of current versus voltage here. And notice how we have our E source value here as our applied voltage, and then our IL is going to be our current here that flows as a result of ideal inductor. So that's one thing that's important to point out here, is that as far as this circuit goes, we're considering an ideal inductor with no resistance. We talked last presentation about an ideal inductor, in fact, doesn't exist, and it always has a small amount, a practical inductor always has a small amount of resistance, but in this case we're considering all inductance, nothing else. And so when we have an ideal inductor connected to an AC source, as you can see, we've got the x-axis of these graphs calibrated in degrees. Right? Now we know that can be calibrated in time, it can be calibrated in radians or degrees. In this case we have it calibrated in degrees. And notice how that when it comes to the maximum value of voltage seen here at time 0 or at angle 0, it takes the current 90 degrees later to reach its maximum value, and what we have is a phase shift here. And that phase shift is 90 degrees. And if we look at the voltage being the reference here, we can say the current lags voltage. So we can say that current lags V. No doubt if you were to take the current as the reference, you would say that V leads I. So when it comes to what we see here, we can say for a pure inductor, that is an ideal inductor, when it comes to the voltage will lead the current by 90 degrees, or put otherwise, the current will lag the voltage by 90 degrees. So if we look at the vector phase relationship between these two quantities, one being voltage and the other being current, notice how here with the current at 0 degrees for a reference and the voltage 90 degrees to the current, we can see that this is referred to as a leading relationship. When you pick current as the reference, this is a leading relationship, and that means that VL leads IL at 90 degrees. Okay. And so this is something called the phase angle. So phase angle for any circuit is the angular relationship between E source and I total. Okay? So that's always what describes a circuit phase angle. The angle between the total current and the applied voltage. And in the case that we had previous of the pure inductor, then we know that with only that as the load in the circuit, the applied voltage will equal VL. So that means that VL and ES, as you can see, are the same voltage here, and that our current is lagging that applied voltage. And this is what would be referred to as a 90-degree phase angle, because it's indicating the angle of the voltage source and the resulting current in the circuit. So then this comes to a very handy acronym that we use all the time when we're studying AC circuits with reactance, and that is ELI. So what does ELI state? Well, first of all, the L in the ELI acronym is indicating that this is for a pure inductor. This is for an ideal inductor. So Eli says that for a pure inductor, or an ideal inductor, that is one without resistance, the current I will be lagging the voltage by 90 degrees. So if we take voltage as the reference, we can see the current, indicated by the acronym, is indicating that it's lagging. And again, the phase angle that describes the angle between the voltage and the current will be 90 degrees. Now what I will say right now is that in terms of these angles of plus and minus, so notice how here it's indicated a negative sign for the circuit phase angle. In reality, circuit phase angles aren't usually assigned a polarity of plus or minus, but it is important that when you consider the phase angle of any circuit, that you express some way or another as to whether it's the result of current lagging voltage or current leading voltage, whereby the type of reactance that's providing the load can be identified. So in this case, if we were to use something like a minus 90 degrees and show the phasors on a phase angle diagram, one would be able to conclude that it's that you have an inductive circuit based on the fact that the current is lagging the voltage. And it's just by applying the Eli understanding to that relationship that allows you to draw that conclusion. So yeah, hopefully that kind of, we'll be going over that lots, but hopefully that kind of just gives you an initial idea. All right, so then we get here to where we look at something called XL. When it comes to reactance, X indicates reactance. So when we have reactance from an inductor, it's called XL, and if we have reactance from a capacitor, it's called XC. So as we look at what we saw previous for the voltage-current relationship, we're going to be able to draw, or essentially conclude, what direction we would show inductive reactance in an impedance diagram. In a diagram where it shows the angular relationship between these oppositions. And just like we've mentioned before, because inductive reactance is an imaginary value that creates imaginary power, it is going to be plotted on the imaginary number line. And for imaginary numbers, we can have plus or minus j. And when it comes to XL, it will be plus j value. So that is to say, if you're asked to give a rectangular value for impedance for any circuit that is primarily inductive, you would always indicate the imaginary value as plus j. Now, to calculate XL, we use the angular velocity times the inductive value, which we know since omega, the angular velocity, is equal to 2 pi s, that can be further expanded to XL equals 2 pi s. Now remember, frequency is in whole units of hertz. XL will result in whole units of ohms, as long as L is in whole units of Henry. So that's what you have to plug into the equation with a value in ohms. So we're really talking about the value of opposition now. Now there's no doubt the value of inductance in henries affects that opposition, along with the rate of change of the angular velocity. But it's important that as we move into reactance of capacitors and inductors, that we understand that there's the opposition from an inductor or capacitor that's called reactance, but then there's the capacitance and the inductance value. And when it comes to inductance, we know that's a value in henries for inductance. Okay, let's look at Ohm's law then for XL. If we consider what we saw in a few slides back when we looked at the voltage and current relationship, we could use that to actually determine our XL value. So if you take voltage as the reference, so if we look here at voltage as the reference at 0 degrees, and we divide it by IL at a lagging 90 degrees or a minus 90 degrees, we know that's the voltage current relationship for an inductor, or a pure inductor, and by using Ohm's law here, we can determine what will be the direction of XL. And when we divide angles, we subtract them, so that would be a minus 90 degrees from a 0 degree angle, which we can see and verify will result in 90 degrees. So as a polar representation, you could say XL is at 90 degrees, or if you're talking rectangular, like we said before, we can say that we have a plus J value for XL. So we have plus J XL. So if we were to actually look at the value of impedance, which we said in an AC circuit can be all resistance, all reactance, or in most cases a combination of resistance and reactance. If we were to look at the ideal inductor that we saw previously in a few slides, its Z total value would be represented simply as plus J XL. The Z total value provided by an ideal inductor would simply be plus JXL, no presence of resistance, and all reactance. Okay, in the previous presentation we talked about L total values, total Henry values from connecting inductors in series and in parallel. When it comes to opposition, or XL now, it's no different than the L total calculations we did. That is to say, when we have a series connection, we simply add up the individual values of reactance, or when we have a parallel connection, we just use the sum of the reciprocals, or a product over sum. So when it comes to inductors, it just lines up with everything we've looked at for series and parallel relationships. We're going to have to be aware that's different when we look at capacitors, but for now, I think the primary thing is to understand is remember that XL is opposition, XL is opposition, or reactance, and L is inductance. XL, its opposition or reactance, is going to change definitely with a different frequency or a rate of change. When it comes to L, its inductance value, remember that's determined by its physical makeup, the number of turns in the coil, the mu of the core of the coil, the length of the coil, and so on. So we got to remember and pay attention to whether we're talking about reactance or inductance. So you can see in parallel, you're just using the sum of the reciprocals, or product over sum. Now, if we take a look at this example then, realize here what we're wanting to figure out is the total opposition of this arrangement. If we were looking at the total inductance value, our answer would be in henries. But here we're looking at a total value of opposition in ohms. So there's a couple of different ways you could approach this. One of them would be to determine the XL values, and then you could say simply XL total would equal XL1 plus XL2, because that's a series connection of two opposition values, added on to, now you're going to use the product over sum here, of XL3 times XL4 over XL3 plus XL4. And that would give you an XL total. Now, of course, there's another way to do this, and this would be to determine the L total value. And of course, if you were to you could do that in the same way. It's inductance or henries you're working with now, right? So it would be L1 plus L2 plus the product over sum value of L3 times L4 over L3 plus L4 to give you your L total value. Now, once you had your L total value, then XL total would simply equal 2 pi F L total. Okay, which would give you the same result as what we had here. So, yeah, that's how you work with inductive reactance. It's a form of opposition, so series opposition is series opposition. Parallel opposition is parallel opposition. Okay, so as combines both inductive reactance and pure resistance for opposition. The combined overall opposition is called impedance. Right? So we know this is called impedance. In fact, impedance is the name we give to any AC opposition, but it could just be resistance, but it's usually resistance and reactance. And in reality, we can't say there is anything in real life that exists as pure reactance, even though we kind of approach it like that at times. It's never purely reactive. There's always some resistance in any circuit. Okay? So, what does that mean? That means that if we're looking at our value of resistance as real, on the real number line, represented as a vector, then we have our XL as a plus J component. It means that we have a Z total value from this example that could be represented as R plus JXL. Now, once that becomes a right angle triangle, then of course I think it goes without saying that Pythagorean's theorem can be used to determine your total impedance, right? The magnitude of your total impedance. So when it comes to this right here, this is going to give you the magnitude here of this impedance. In order to determine the angle here, which would be called angle phi for the angle of impedance, then when we have that, then that can be determined using trigonometry, or what I would suggest is going to be your most efficient way of doing this is learning to use your calculator to do polar to rectangular conversions and vice versa. So that means here we'd have the rectangular version, and so if you were to convert that to a polar version, you'd end up with a Z and angle phi or phi, right? So make sure you're up on that with your calculator and doing those conversions, because that avoids you having to work with the Pythagoreans and the trigonometry and all that kind of stuff. Okay, so let's just take a simple example here. Here's where we have a series connection of R and XL. Notice how in this case you didn't have to calculate XL, it was given to you. So another example of this problem could be where you've been given a value of L for this coil and a frequency from the source, and you have to calculate it yourself. Remember, if you're not given a frequency for a source, you're to assume 60 hertz. And if you're not given if you're not told otherwise, you're to assume RMS for your voltages and your currents. Okay, so if we look at this example, first thing we need to understand in approaching total impedance here is that we're working with a series circuit. Now, that's important because we have to kind of back up for a minute and not get clouded by these details, and remember that when you're talking about a series circuit, that's when you can add oppositions directly in order to come up with total opposition. If these two components were in parallel, we couldn't approach it the same way. But because they're in series, and we simply add the values together to determine the total opposition, we can simply say in this example, Z total is going to equal our R value plus a J value of XL. So therefore, in this case, it could be written as 5.6 k ohms plus J 10 k ohms, right? That's going to tell us our total impedance. So if we were to draw that in a triangle indicating the impedance triangle, remember this is a series arrangement, so we can do this directly from the values given. We have 5.6K shown as our real value of resistance. We see our plus J value of 10K ohms here. And then we can see our hypotenuse, which is our total magnitude of impedance. And there's two ways we could express this impedance. First of all, as its rectangular value of 5.6K plus J 10K ohms, or 11.5K ohms at an angle of 60.8 degrees, Z total value. One of them is the rectangular value on the top, and then on the bottom we have its polar value. You should be able to, in your calculator, toggle back and forth between these two values based on knowing how to use your calculator. So when it comes to the angle of impedance, truly when we're talking about the angle of impedance, it's something we call phi or phi. Now, as it turns out, the angle of impedance, or phi or phi, is always equal in magnitude, but opposite in, you could even say polarity, I suppose, but opposite in the leading or lagging relationship. So it means that when we have an inductor, and we go back to looking at this impedance triangle, notice how in terms of our real resistance here on the real number line, our impedance is leading. So we have a leading impedance, right? A positive angle. But when we divide that into our applied voltage in order to give us current, we notice that we had a lagging current from an inductor, didn't we? And that was supported by the acronym ELI. ELI is telling us our current will be lagging our applied voltage. Well, how did we end up with this lagging relationship for current? Well, it was the result of a leading impedance. Okay? So, if we go back here, angle impedance, both phi or phi, is always equal but opposite to angle theta. Now, often, because of that, and because I said that really polarity is not overly important in AC circuits when it comes to expressing the phase angle, what's more important is you understand whether the phase angle is the result of inductance or capacitance. Often the angle of impedance and the angle theta are just used back and forth without specifying specifically phi or theta. So total circuit current can always be found by dividing the applied voltage by the total impedance. Don't forget that. It doesn't matter. Is it series or is it parallel? Doesn't matter. If you have determined the total impedance and you have the applied voltage, this will always apply. As you know, this is Ohm's law, so we're not going to be rewriting that or changing it. It's always going to apply. Okay, so if we take this example right here, you can always pause this and go through this process on your own. But what's the first thing we need to understand when we look at this circuit? Well, first of all, we can see we have a series connection. So because we have a series connection, it means we can take a value of R that we see here as 1 k ohm. We can calculate a value of XL based on our angular velocity or our frequency, and notice we have to pay attention that we've got a frequency of 10 kilohertz here for the purposes of this exercise. And we can calculate the XL value now. But because it's series, we know we can add those oppositions up directly. So let's just review what we know here. The voltage across the resistor and the current are always in phase. So this is what we need to understand about a resistor. A resistor produces real power. It does real work. And that happens when we have a 0-degree phase angle between voltage and current. That means they're synchronous. So that means if I'm looking at the voltage waveform for a resistor, and I'm looking at the current waveform, they're synchronous, right? So that's a 0-degree phase angle. That's 0-degree phase angle. And they're always in phase, and we'll never change that. So when it comes to any resistors in an AC circuit, we can always say their voltage, the resistor voltage, VR and IR are in phase. When it comes to any inductor in a circuit, we can say Eli is the case. So the voltage across the inductor leads the inductor current by 90 degrees, or an inductor current lags the inductor voltage. For a series circuit, we know KVL applies. So that means we have to be able to add the voltages together to equal our source voltage. Likewise, when it comes to a series circuit, we know that our common quantity within the series circuit is current. So that means that our I total value is going to equal our IR value, is going to equal our IL value. Okay? Now notice how it says I total is our reference. That is the reference in, as you know, because we've studied this in previous circuits, you can move the reference around to wherever you want. Double subscript is an example. The second letter is your reference for double subscript. It's kind of the same idea in AC. You can assign whatever reference you want. In power systems, it's actually very common to have the applied voltage as the reference, because in power systems everything's about the voltage. The distribution voltage in your neighborhood, in the substation, the transmission voltage, the high voltage, the generator voltage, everything is all about the voltage. So it's very common to have the voltage as reference in power systems. In electronics, not so much, but in power systems, that's very common. So we have to be prepared to work with different references in any circuit. So when we go to the next slide here, it's saying the angle made between the total current and the applied voltage is called the circuit phase angle, and we mentioned that before, and we represent that as theta. So that's indicating the circuit phase angle. Now again, I said you can assign polarity to these angles, but what's most important, like I said, is really understanding whether the phase angle was the result of an inductive circuit or a capacitive circuit. And in this case, we know we're working with XL or inductive reactances. So because of that, we would definitely call that a lagging phase angle with respect to the applied voltage, because remember, we have to, if we're going to use that term, we have to have a reference. And this is going to be with respect to the applied voltage in this circuit if we're going to express the current is lagging. So we would say we have a lagging or negative angle if we use the applied voltage as a reference. Now hopefully that makes sense, because if we chose the current as a reference, then of course you could say that the voltage was leading that. So let's take a look at what we would see for the voltage triangle. So first of all, remember we have an I total value that we know is going to equal IR, that we know is going to equal IL. So notice how here, that value of current, that one and only current, because it's a series circuit, is being represented here. Right? So just let me get rid of that for a minute. So when it comes to the I total value that we see here, that's the common current value for this circuit. How did we end up with a value of VR here? Well, remember, we said that for a resistor component, that voltage and current are in phase. So that means if I take the value of I total and multiply it by R, then I total at 0 degrees, in this case 0 degrees, multiplied by R at 0 degrees is going to give me a IR value at 0 degrees. And that's what's going to give me my VR here. What about VL? Well, if I'm continuing on with I total at 0 degrees because it's the same current, then my VL will be determined by I total times XL. But remember, XL is a plus J component. So with XL being a plus J component and multiplying by that current at 0 degrees, notice how we have a VL value here that is 90 degrees to the 0 degree current. And then what's that going to mean? That's going to mean that we can express our ES, or our source voltage, as a Kirchhoff's voltage law, VR plus VL. So notice how that's what we have here, a VR plus a JVL. Okay, so this is a series voltage triangle and proving Kirchhoff's voltage law for this circuit. What does that mean when you have series impedance? Well, it means that the impedance triangle is going to look just like the voltage triangle, because don't forget, each one of these quantities, R and XL, is multiplied by the same current in order to get voltage. So we're going to have a voltage triangle that looks just like the series impedance triangle for any example. Okay, so if we look at this example, let's get you to work on that, and while you're doing that, on the next slide, I'll indicate the answers. But this is an example of going through what we talked about, using frequency to determine the XL value from L, and going about proving Kirchhoff's voltage law after determining VR and VL, using your impedance triangle to determine total Z, and therefore using your angle phi or phi and your theta to indicate the circuit phase angle. Now, of course, your total impedance, when divided into your source voltage, is going to give you I total. Okay, so here's the answers we see. Total impedance given here in your impedance triangle. And here you can do another example to come up with results. Okay, so let's finish up with the parallel here, and then we can move forward to doing the practice. So if we look at this parallel circuit, what do we need to understand? Well, we can't add these oppositions directly together like we could in series, and that's really important. If you were to tell me you could take the values here and put them together directly as a rectangular value by simply adding them together, you'd be telling me that two 10-ohm resistors in parallel equals 20 ohms, and I know no one will tell me that. So don't forget, when it comes to this, we have to come up with our total impedance by sum of the reciprocals or product over sum. So that means in this case, well, how would you determine Z total? Well, Z total just has to be determined by R multiplied by XL over R plus J XL to give us a product over sum value. This would be product over sum, and this would give us our Z total value. You have to understand that because it's parallel connections. You can't just add them together like you could when they're in series. there is another way to come about or verify your impedance in parallel, and if you think about it, it makes sense, is that if you determine your IL branch current here, and then you determine your IR branch current here, if you simply add those together, which you need to do for Kirchhoff's current law, you can determine I total. The thing you need to understand, of course, is that these two currents are not in phase. Remember, this guy is an inductor. The first branch is an inductor. So that means when you divide a plus JXL value into this applied voltage to give you IL, that current is going to be a minus J value. Right? This guy is going to be a 0 degree value, IR. So when you're going to add these two together, when you're going to come up with a total current value, your total current, I total, would be your IR plus minus JIL plus minus JIL, because we have a lagging current here. So that's going to be the way that you determine your total current. Now once you have your total current, don't forget Ohm's law will still always apply, won't it? And Z total will have to equal E source divided by I total, right? So you have your I total value from up here. So what does that look like then? Remember, in a parallel circuit, we have this relationship for voltage. E source equals VR equals VL. It's our common quantity. Remember, because we said, just like back in a few slides back, is that voltage and current for a resistor are in phase. That means that with VR being found right here, that IR has to be right in phase with it, a 0 degree phase angle. And from the previous circuit, you calculate that as 20 milliamps. And our lagging current, 63.65 milliamps. You know that the Kirchhoff's current law says that the result is going to be adding the two together. And so you can do a rectangular to polar conversion, and you'd have obviously two representations for I total. If you're looking at representing it as a rectangular value, it would be 20 milliamps plus, or you can go directly to minus J 63.65 milliamps, or that could be expressed as 66.72 milliamps at an angle of minus 72.56 degrees. This one being polar, this one being rectangular. So last thing I'm just going to bring to your attention is something called a phase angle diagram. Now, a phase angle diagram is kind of unique because in an impedance diagram you have all impedance vectors. In a voltage diagram, voltage triangle, you have all voltage values, and in current, all current. But when it comes to a phase angle diagram, remember, phase angle is the angle between the applied voltage and the total current. So this is what we see as an example here. We see the applied voltage is 120 volts VAC, just as an example. The total current as 10.3 amps, and the resulting phase angle here, theta, of 42 degrees. Now, this is indicating a lagging current, right? And so, based on the fact this is indicating a lagging current, we know that this would have to be a circuit that is primarily inductive. So it's got more inductance than it does capacitance, and that's why we have a lagging current, just like the Eli relationship indicates. Okay guys, well that's enough for now. We'll be doing some more practice. I have a couple of practice exercises ready.